is the efficiency. Output in general is going to mean power output over power input, right? And then, so that means the power input is going to be the power out over the efficiency. And then the power input is going to be the amount, like, you could easily say, like, kind of like the work over the time. I didn't even write down what we're supposed to. That is like my biggest weakness. What are we supposed to find? How many kilograms of water? So the number of kilograms of water required to create this much external energy. So that much external energy tells us that we need this much energy going in. And then this much energy going in, how do we get that from this? Does it tell us per kilograms per whatever? Yeah, okay, kilograms per second. Yay. So kilograms per second. So then all we need to do is take this potential energy, because we know that 1 kilogram gives us this much energy, right? And then just divide the power in by that. So how do I write that? Oh, yeah, I can just write it. I'm going to write all this out. It's all don't matter. So basically, it's just the power in divided by delta U per delta U sort of unit. Right? So then that will cancel with this, and then I'll be able to get everything. So if I want to do this like a giant thing like this, I would go, we want the number of kilograms, and we have the power out. So I would say the power out, so the power out's in watts, so this will be the power, no, that doesn't work, power in, and efficiency, no, that doesn't work. So if we do it step by step, if we want, just take the power out divided by the efficiency, so that's going to be 80 times 10 to the 6 watts divided by 0.8. Right, so then that becomes 1 times 10 to the 8th watts. Is that right? To the 8th? Yeah, because this is 80 divided by, hub mega is 6, yeah. So this is 8 times 10 to the 7th, and then 8 divided by 0.8 is 10, right? So that's 10 to the 7th, which should give us 1 to the 8th. Questions about that part? And so this is in joules per second. And then we know that that delta U we already calculated was 250 joules. Right? The water loses that much, which means the power plant gains that much energy per kilogram. So it's 250 joules per kilogram. So if we, and then we know that the time is 1 second. So the amount of energy is equal to 1 times 10 to the 8th joules. And if we divide that by 250 joules per kilogram, yeah. Oh, 50? Okay, I just wrote it wrong. Times 10 to that, and then 50 into 8 is 6.
6.25.
6.25? Okay, so that becomes 6.25 times 10 to the, is it still the same thing? 10 to the, 10 to the 8th, right? Because 50 is 5 times 10 to the 6th.
Yeah, but then that's
and then because it's divided.
That's 8 over 10. So
yeah, so it becomes 5 times 10 to the 8th divided by 8.
Isn't it divided by 7?
It's already 50 times 10 to the 6th, right?
Yeah.
So that becomes 5 to the 7.
Dividing 50 by 8, not 5.
Yeah. if you do 50, if you do this, move this over, and that becomes 500 divided by times 10 to the 6th. Yeah, you know what? This should be 7. Because if it's 5 to the 8th divided by 8, then the answer will be this. Okay, there you go. So this is 6 1/4 times 10 to the 7th, 250 to the 7th. So whatever, divided by 250, what do you get? Oh yeah, it's like 25 squared. 2.5 times 10 to the 5? That makes sense. 2.5 times 10 to the 5th kilograms. So basically just take your energy output, convert it to energy input, and then take your energy input, and because they're interested in 1 second, that energy input becomes joules instead of watts. It becomes an energy instead of a power. And then just divide that energy by the energy per kilogram, you get the number of kilograms. I think you could solve this in one big giant, like one of those conversion thingies if you wanted. Giant stoichiometry thing.